All right, if you're gearing up for your STAT 202 exam, you are in exactly the right place. We are going to dive deep into the Anova questions from your practice exam, and we'll be using the Montgomery textbook to make sure we understand all the theory behind them. Let's get you ready to absolutely master this stuff.
So here's how we're going to tackle this. First, we'll get to the heart of what Anova is even for. Then we're going to pull apart that famous Anova table. After that, we'll talk about the F-test and the p-value, which is where we make our decision. We'll see what to do after the F-test, then cover the common traps you need to avoid, and finally, we'll wrap it all up with a solid game plan for your exam. Okay, first things first, before we even think about touching a formula or a calculation, we have to be absolutely crystal clear on what ANOVA, what analysis of variance, is actually trying to do. This is the fundamental why that drives everything else. So let's start with a really foundational question, number 30 from your practice sheet. It asks, ANOVA is a statistical procedure used to compare the blank of different groups. Your options are means, variances, sample sizes, or standard deviations. And the answer, the absolute core idea of ANOVA, is A, means. And, this is where the name analysis of variance can kind of throw you off, right? It's a bit of a head fake, because even though we are analyzing variances to get our answer, our ultimate goal, the whole point of the exercise, is to compare the means. We do this by figuring out if the variability between our different groups is significantly larger than the variability within each of those groups. Okay, so if we're all about testing means, we obviously need a formal hypothesis, and you can bet your exam is going to test you on getting the wording exactly right. So let's look at question 11 to nail this down. Now, question 11 gets at one of the biggest and most common traps in all of hypothesis testing. Our hypothesis is never about the sample means, the ones we can actually see and calculate from our data. No. It's always about the population means, the true underlying averages that we can only infer. We're using our sample to ask, do the differences we see in our data point to a real difference out there in the whole population? So the null hypothesis, H0, is that all those true population means are equal. The alternative is simply that at least one of them is different. And if you look in the Montgomery textbook, you'll see this written in a more formal, statistical way. It uses the Greek letter tau for what it calls the treatment effect. So when it says the null hypothesis is that all the taus are equal to 0, that's just the fancy way of saying that none of the treatments have any effect, which means, you guessed it, all the population means are equal. All right, section 2. Let's get into the engine room of ANOVA, the Anova Table. Now, I know this can look a little intimidating at first with all the boxes and letters, but trust me, it's just a worksheet. It's a super organized way to do our calculations to get to that one magic number, the F statistic. We're going to break it down piece by piece. Okay, so question 7 on your practice exam gives you this exact scenario, a half-filled Anova table. This is a classic exam question, so you need to get comfortable with it. The best way to think about it is like a logic puzzle. They give you just enough clues to figure out all the missing parts, as long as you know the rules of the game. And here are those rules straight from Montgomery. It's actually pretty simple. First, the two columns on the left, degrees of freedom and sum of squares, they just add up. The groups row plus the error row equals the total row. Simple. Then, to get the mean square, or MS, you just divide. It's the sum of squares divided by the degrees of freedom for that same row. And finally, the big one, the F statistic is just one MS divided by the other. MS groups on top, MS error on the bottom. So let's use those rules right now to solve question 7 together. Step 1, find the missing degrees of freedom for the error. We just subtract, right? Total minus groups. So 20 minus 5 gives us 15. Easy. Step 2, same logic for sum of squares. Total SS minus error SS. 683.2 minus 453.6 is 229.6. See? It's just a sequence of simple arithmetic. Step 3, now we calculate the mean squares. For the groups, we take its SS, 229.6, and divide by its DF, 5, which gives us 45.92. We do the same for the error row, 453.6 divided by 15 is 30.24. And the final step, step 4, calculate F. We just divide those two MS values we just found, 45.92 divided by 30.24, and we get our answer, 1.52. And hey, let's connect this to some other questions on your exam, because they love to test the same concept in different ways. See that degrees of freedom for error we just calculated, 15? Well, the formula for that is always n minus g, where n is your total number of observations and g is the number of groups. And if you look at questions 34 and 42, yep, that's exactly what they're testing.
See how it all links together?
Let's zoom in for a second on that mean square error, or MSE, because that's what question 9 is all about. What is it? Think of MSE as our best estimate of the natural, random, unexplained variability within each group. It's the background noise in our data. It's the yardstick we're going to use to measure whether our treatment effect is actually significant.
Okay, so we've done all the hard work. We filled out the table, we found our F statistic. Now for the payoff. This is the most important part. How do we use that number to actually make a decision? This is all about the F test and its partner, the p-value.
In question 49 gives us a really fantastic, super intuitive way to think about what that F statistic actually represents. It's a ratio. That's all it is. It literally measures how many times bigger the variation between the groups is compared to the variation within the groups. It's our signal-to-noise ratio. Is the signal from our treatment strong enough to be heard over the background noise of random chance?
And that directly answers question 10. Think about it. If the null hypothesis is true, meaning there's no real difference between the groups, then the signal should be about the same size as the noise, right? So our F statistic should be somewhere around 1. But if the alternative hypothesis is true, and there is a real difference, then our signal is going to be stronger than the noise, and our F statistic is going to be greater than 1.
And this right here, this is the golden rule for making your final conclusion. This is what you need for questions like 8 and 35. You take your p-value and you compare it to your significance level, alpha, which is usually 0.05. If the p-value is small, smaller than or equal to alpha, you reject the null hypothesis. The data is screaming that there's a difference. But if the p-value is large, larger than alpha, you fail to reject it. The evidence just isn't strong enough.
Okay, let's apply that rule right now. In question 35, they tell you the p-value is 0.481. So, what's the call? What do we conclude? Just take a second and think it through based on that rule we just laid out. All right, here's the play-by-play for question 35. Our p-value is 0.481. That is way bigger than a typical alpha of 0.05, right? So since p is not low, the null can't go. We fail to reject the null hypothesis. Now look at the options. The correct conclusion, which is option C, is very carefully worded. It says we do not have sufficient evidence to say the means are different. And that's the key phrasing. So that's what happens when the p-value is big. But what about when it's small? What happens when we do reject the null? A significant F test is kind of like a fire alarm. It tells you there's a fire somewhere in the building, but it doesn't tell you which room. That's where post-hoc tests come in. They're the firefighters who go room by room to find the source. So your exam gives you this bar chart. It's from a study on rats, and they're comparing 4 different diets to see how they affect motor skills. We've got a control group, and then groups that got strawberries, spinach, or blueberries. A higher bar means better motor skills, and right away, your eye is drawn to that blueberry bar, isn't it? It looks way better. But we can't just trust our eyes. We need the stats to back it up. So let's say we ran the numbers, and the overall Anova F test for this data came back significant. The p-value is tiny, so we rejected the null hypothesis. Awesome! But that just leads to our next question, right? Which groups are actually different? Is blueberry really better than control? Is there any difference between spinach and strawberry? We need to zoom in and do those specific pairwise comparisons. And this is a super common way you'll see the results of those follow-up tests, these post-hoc tests. You'll see these little letters above the bars. And the rule for reading them is incredibly simple. If 2 bars do not share a letter, they are statistically significantly different. If they do share a letter, they're not. Let's apply that rule to our chart. Okay, look at control, strawberry, and spinach. See how they all have the letter A above them? They all share a letter. That means, statistically, we can't say there's any real difference between those 3 groups. Now look at blueberry. It only has the letter B. Since blueberry, B, doesn't share a letter with any of the others, A, we can conclude that the blueberry diet led to significantly better performance than the other 3. Now, question 20 gets into a bit of the nitty-gritty and asks why we use a pooled standard deviation for these kinds of tests. And the key reason goes back to one of the main assumptions of ANOVA. ANOVA assumes that all the groups have roughly the same variance. So, by pooling the data from all the groups together, we get a single, more stable, more robust estimate of that common variance. It just makes our test more reliable. Okay, let's move into a really, really important section. We've gone over how to do the problems correctly,
But now let's talk about the easy mistakes to make, the common traps, and misunderstandings that can cost you points on the exam. Honestly, knowing what not to do is half the battle. Trap number 1, and we've hit this before, but it's worth repeating. Confusing the population with the sample. We saw this in question 11. The null hypothesis is always about the population mean mu. It is never about the sample mean x bar. Remember, we use the sample we can see to make an educated guess about the population we can't see. Trap number 2 is a big one, messing up the interpretation when you get a non-significant result. You have to be so careful with your wording. Failing to reject the null is absolutely not the same thing as accepting the null or proving the null is true. A not guilty verdict in a trial doesn't mean the person is proven innocent, it just means there wasn't enough evidence for a conviction. Same here. We can only say we lack sufficient evidence to conclude the means are different. And trap number 3, which is what question 29 is getting at, is misunderstanding the word error. In statistics, especially in Anova, error does not mean you made a mistake. It has nothing to do with a miscalculation. It's just the statistical term for all the natural, random, unexplained variation in the data. It's the background noise that isn't accounted for by the different groups you're testing. All right, deep breath. We've covered the concepts, we've walked through the calculations, and we've flagged the common pitfalls. Now let's pull all of this together. Let's create a solid, concrete game plan you can take with you into the exam. This is your mental checklist for any Anova problem they throw at you.
Here it is, your 5-step process for Anova. 1. State your hypotheses. And remember, they're always about the population means. 2. Build your Anova table. Just remember that the sum of squares and degrees of freedom columns add up. 3. Calculate your F statistic. It's always MS groups over MS error. 4. Find that p-value and make your decision. If p is low, the null must go. And 5. If and only if you reject the null, then you move on to post hoc tests to find out exactly which means are different.
And just to really drill it home, here's a little summary table of the must-know formulas and the specific practice questions they'll help you solve. You need to know n minus g for the degrees of freedom for error. That's for questions 34 and 42. You need the F statistic formula for 7 and 43. Understand what MSC is for question 9, and of course, know how to write the null hypothesis for question 11. If you know these, you're in great shape.
So, here's my last piece of advice for exam day. When you turn the page and see that big Anova table staring back at you, just take a breath. Don't let it intimidate you. Just remind yourself what it really is. It's nothing more than a structured, organized way to compare the signal, the variation between your groups, to the noise, which is the natural variation within your groups. That's it. Signal versus noise. And I'll leave you with one final thought to carry with you. We've seen just how powerful Anova is for comparing means across multiple groups. It's an amazing tool, but its power and its validity depend on a few key assumptions we have to make about our data. So, for the results of an F-test to be trustworthy, what are those assumptions? What has to be true about our data's distribution, its variances, and the independence of our samples? Thinking about that, that's the next level of statistical understanding. Okay, good luck on the exam. You've prepared for this. You've got this.